Swayam Prabha. Digital India. Educated India.
Welcome back to this lecture series on cyber physical systems. So, in the previous lecture we have been talking about some possible security issues in cyber physical systems, what can be possible attack models, and how the attacks are modeled mathematically in terms of perturbations on variables y and u, and more importantly we also showed the example of a practical attack, that how the CAN bus is really vulnerable and how attacks can be implemented to take offline some specific ECU. So, what is important to understand is attacks will keep on happening on cyber physical systems because they are of real value to the society, infrastructures and everything. Such critical infrastructures need protection, right? I mean, not only infrastructures, real automotives and other systems, they all need protection. So, how can attacks be detected? Now, of course, the strategy that will definitely come into everybody's mind is that, well, we have so much mathematically well known cryptographic methods for data protection, right? So, you have algorithms like AES and advanced encryption standard, you have RSA, some hash algorithms, etc., which give you this guarantee of authentication. I mean, for authenticating a data that is received from the sensor, and also to check whether to check the data integrity, whether where the data has been perturbed or not, right? So, what can be done is, you have a measurement, you first encrypt that measurement with, let us say, a 128-bit AES kind of crypto algorithm, and then this data you also to protect the integrity of the data, you add a message authentication code or CMAC using a CMAC hash algorithm, right. So, you can add AES and MAC together. So, with AES you have data authenticity, because on the receiver side the data can be decrypted, right, and the original data can be obtained. So, you know that, well, who is the sender of this data, and also using the MAC you can actually check that, well, the data is okay or not. I mean, because even if you encrypt and decrypt data, it may so happen that the data is perturbed, right. So, that is why we will also need the integrity check, and the integrity check can be done by an HMAC algorithm, some message authentication hash algorithm, right. But what is the problem here? The problem is, doing all these things take up resources. You need to run this AES algorithm and the hash algorithm at the same speed as the period of the data, if you want to actually encrypt every packet, right. So, if age is the period, with every inside every interval of size h, let us say this is your data stream, and you have a data point here, a data point here, these are all m bits, and this is the interval h. That means, you are adding an additional task of encrypting these m bits and then doing a MAC on that, right, this original encrypted data, and then this has to be done once every h period, right. So, that is a lot of compute that we will need to do. So, that will increase your your computational footprint on the low power real time systems, which may not allow that, and more importantly your communication overhead will increase a lot. So, that is the computation overhead we talked about, and now what about the communication overhead. So, it can be shown that if you have a CAN message and you do a 128-bit AES encryption and this HMAC comparison, HMAC based algorithm for a standard payload size of a CAN message, then the amount of bits that will be in effect you need to transmit, since your number of bits will now increase due to this AES encryption, right. So, effectively now for every original CAN packet you will need to convert them to 6 CAN packets, So, it is not only that you have to invest resource for doing the computation, your message bandwidth needs to be significantly more. Right now, that may not be an acceptable solution for low resource real time communication and processing. Okay. So, here we have an example where we are trying to show that at what conditions this will happen. So, let us say you have a 64-bit CAN payload message M. So, this is your sending ECU. So, it will implement this SHA-2 based algorithm for doing this message authentication. Okay. And then this will generate 256 bits. Okay. Because your original 64-bit CAN, you have to append this 256-bit MAC, right, and that would create this 328-bit payload. Okay. And on this, you will, if you will run this 120 AES 128 algorithm, you will effectively have this 384 bits payload. Okay. Now, if you consider this CAN packet size to be 64 here, right, then effectively what you have is something like this. So, you are running AES 128. So, effectively let us say you have this 384 by 64, it is effectively 6 CAN frames that you are kind of generating. So, you have on the CAN bus, you have to send these AES blocks, and not only that, on the reception side you will have first a decryption task, right, and then after doing this decryption you will have the message and the message authentication code together. You will separate them out, and then you will do this hash algorithm of the hash computation, and then you will check whether the hash matches with the original HMAC. Okay. So, all these new tasks have to be executed, and not only that, the original CAN payload, which was 64 bits, 64 bits CAN payload. Now, this would result to this I mean you will essentially have this after you append this 256 bit MAC, you will have 320 bits payload here, and once you do this encryption, you will have a 384 bit payload here, right. So, with this 384 bit payload, now when you are transmitting this over the CAN bus, you will have to divide it into multiple CAN packets, right. So, essentially you will have this 384 divided by 64, right, because that is the size of your CAN packet. So, effectively you will have these 6 CAN frames here. So, we understand this cannot really be a solution. Okay. So, since this cannot be a solution, what can really be done is you can actually use lightweight statistical detectors, which will try to correlate the value of different messages and see that, well, there is a strong correlation, or not. Okay. Now, for building such lightweight detectors, what we do is we will exploit the control theoretic properties of dynamical systems, because we have one weapon here, which is that we know the model of the dynamical system. That means, we know that, well, if we give this input, let's talk in a very simple manner. Let us say this is your plant, and let us say this is now your control input, and right now your plant state is x. We know that, well, x could go to x plus 1 or some updated state, and from that I will get a y k plus 1, and we can actually estimate that, well, what I am expecting x to be and what I am expecting y to be. Okay. So, this is x k plus 1 and y k plus 1. I know that, well, for this x, if I mean based on the current measurement that I observe, if I give this much value, what do I expect as an output? I have an idea about that based on my estimation, based on my knowledge of the physics of the system. For example, if I have a vehicle driving at a speed and I give this much of brake, I know that in the next cycle the vehicle speed must be lesser than what it is now, and it should be lesser by maybe maximum of this amount. I can estimate that, right. So, I can use these kind of mathematical estimators to figure out, well, what should be an expected value, and then I can correlate it with whatever value I am observing, and I can see this difference between the estimated and the actual plant output, and that can be used to detect whether there is a false data injection type of attack or not. So, if we just put all these things in a mathematics, so under no attack scenario, this is your system, right, x k, y k is the estimated output x k hat, etc. So, this is your equation of the system update with process noise. This is your equation of measurement with measurement noise, and you know that well there may be a difference between this estimation and whatever is my measurement. So, I will have this residue, right, and based on the Kalman filter gain L, I will have this equation for the observer system, and I will have this equation for controlling for the control input computation. Okay. Now, when there is an attack, what is happening is we just replace these original variables with their attacked variable variant. So, what we have is, let us say this an amount of attack that is happening on the system. Let's start to characterize them. So, we will say that let us say on y the attack is modeled in this way mathematically, that original unperturbed value of y is y k, and under attack we call it y k a. So, we are putting in a superscript on every variable that is either directly attacked or that is getting modified due to attack on other variable. So, let us say the direct attack is happening here, and similarly on u k we have u k tilde, right, under attack we u k a, that is how we will write it. So, these are the under attack variants of the variable names, and now we also need variables to model the amount of attack. So, we model the amount of attack that is really taking place on the y and the u using these two quantities. So, let us understand there is some attack happening here, there is some attack happening here, due to which these values y's and u's are changing, and that is why we add this attack subscript. But we also need to tell, well, how do I model the amount of attack? So, fine, that can be a total replacement of the whatever is the current value, but the way we model it as is an increment of the current value. I hope that is clear, that what I am saying is, well, the attack need not be a perturbation over the current value, right. If that is the case, we will have the current value plus some unknown value added. It can, the attack can even be that I totally disregard the current value and add a new value, right. So, then what the mathematical way to model it would be that you set y a k to be 0, and then you just have this y a, this a y k, which is the new value, and that itself is the amount that the attacker is injecting, right. So, when I do it mathematically, we are saying that the under attack y is nothing but the original plus this increment that is being added as a perturbation, and under attack all my equations are changing with this a superscript. This equation is also changing because they are all working with attacked values. So, we are introducing that a superscript. The control input is also working with an attacked value, right, and then whatever is computed here it's superscripted because, well, let us see the sequence here. So, if we see the sequence here, let us go through this once again. So, we are saying that, well, there was some value that was injected here due to this y changed. Now, due to this change of y, what will happen is my residue will change. Due to this change in residue, what will happen is my x hat will change. So, that is why the a superscripts are coming in an interdependent manner, right. So, this is attacked, its effect is felt here, that effect is felt here, now that effect will be felt here. So, that is why I am superscripting this one here, and then since x has got modified and u has got modified, there is also an additional thing that can happen is the attacker can add perturbation here. So, this perturbation is modeled using this variable a u k, right. So, what we do is on this attacked version of u, you also add the a u k, and then you represent this using this tilde. Okay. So, let us understand this mathematical symbolism. We are introducing attack here in the y, and the effect of that percolates through r, x hat and up to u. That is why we are superscripting r, x hat and u with this variable value variable a, right. And then we are also saying that, well, not only u is superscripted with a, but on due to, so this superscript is coming due to the indirect effect that y brings in, the ayk brings in. Okay. But apart from that, you can also add a real attack value to the control signal itself, and that is this auk, right. So, this one has a superscripted to model the effect of the measurement perturbation ayk, and due to that by this chain of events the control input has got modified. And not only that, on this modified control input you can again perturb it further more, because that is what the attack model here allows you to do, because you can perturb here as well as here, right. So, you can add something additionally. Now, if you add this, then the output cannot have the same symbol. So, you add this tilde here, right. So, that is it. Now, you have this u tilde ak as the perturbed control input, which is really flowing into the plant. I am repeating, this has two perturbation components. One is the disturbance that percolated due to this ayk attack. Due to that, y changed, r changed, x hat changed, u changed. On this changed u, you further you can add this amount of attack here, and then you get u tilde ak plus 1, and this effect will now go into the plant's dynamics, and that is why the plant's overall dynamics under attack will be affected by y in an indirect way, and this in using this ayk and also with this auk. Okay. So, I am just trying to tell why on u I both have a tilde transformation and a net transformation. One is due to the indirect effect of the attack ayk, and also due to the direct effect of this attack auk. Okay. So, this is how I am mathematically capturing the effect that can come to the dynamical system due to these attack perturbations that can be injected both here and here. So, once this happens, we have the following situation, that you can add a residue based threshold based attack detector. So, what it does is, well, you see we are computing this, right, that is the residue under attack. So, you actually you have an estimate, right. You can based on your current observations, you see your current measurement, based on your current measurement you can you have your this, right. Based on your previous measurement of y, you actually computed an estimated state based on, let us say you had an observation of earlier, you had an observation of y a k minus 1, right. So, based on that y a k minus 1, you computed residue r a k minus 1. So, based on r a k minus 1, you have computed x a k hat, right. So, once you receive y a k, you can use y a k here, and you can use that previous computations x a k hat here, and you can compute the residue. So, this c x hat a k is nothing but y a k's estimate, right. So, just like you have the original measurement, you can have this estimate here. So, this c x a k hat is written here as y a k hat, right, and you are comparing y a k hat with y a k, and you are seeing that, well, whether this difference is too much beyond some preset threshold th. So, I hope this is clear. What we are really doing is we are having a detector circuit here, which is looking at the current measurement, right, and based on the previous measurement it has estimated its previous based on the previous measurement it has an estimate of the current state, and based on the current state it also has an estimate of the current measurement, right, and it is comparing this difference between what it estimates to get under attack and what it is actually observing, right. Now, see that earlier also there was this attack, but had it been the case that in this cycle there was no attack, then whatever I am measuring here right now and whatever I am estimating based on my previous attack estimate would be very nearby. Let us understand this. Suppose there was this attack happening in the previous cycle, and due to that I computed the residue, but now in this cycle there is no attack. So, based on the previous cycle's attack I got some previous erroneous measurement. Due to that measurement there was a residue, but due to that residue I also estimated what would be the state in the current cycle, and this state will not be perturbed, let us say in this cycle. Then in that case whatever I will get as an estimate of measurement for this cycle and whatever I capture as an actual measurement, that difference won't be much, because I am considering that there is no attack. But if there is a significant attack here, that difference will be beyond some threshold, and this detector will raise an alarm and it will sound that, well, there is really an attacker present in the system. Now you see that with respect to doing all this crypto computation that we did here, doing this check is simpler. It is just a set of equations which are anyway getting computed here because of the estimator, controller, etc. All you are doing is you are computing the residue, which is also a part of the Kalman computation here, the estimation here. But now you just you use this residue in a comparator and you check whether this residue value is too much or not. So that's your detector, right? So such detectors have actually got wide application in several kinds of CPS systems, because they are very easy to implement and they may be effective also. So it can, I mean, the detection can be of two types. They can be also more involved. The simplest one is the stateless detection, where we will raise this alarm for every single significant deviation at the time k. At every time step k, whenever there is a significant deviation beyond the threshold, we will be raising an alarm. So it doesn't remember the previous state or whatever, right? So it's, I mean, so in every cycle I do this comparison, and if I see that there is an issue, I will raise the alarm. So that's stateless detection. Stateful detection means I will compute an additional statistic which keeps track of what are the historical changes of residue, because maybe in previous cycles the residue changed by a small value, but maybe that was the attacker's intention. It is changing the perturbation with very small values, so that in every cycle the residue is not too much. So the attack is actually escaping the monitor, but slowly the dynamics of the system is shifting from some threshold, from some set point. So that's more like a zero dynamic attack with continuous perturbations of very small values. I am slowly diverting the control system from a set point to somewhere else, but nobody gets to know that. So to thwart such an attack, what I will do is, well, whatever has been the earlier changes, I am summing them up, and maybe so doing sum is one possible way to keep track. That there can be other I mean non-memoryless stateless detections also. Okay, so let's say I am just using a simple technique. I am just summing the residues, and so that is one kind of statistics I can generate, and I will eventually compare, well, what is the accumulated residue if that is greater than a threshold or not. So that's like a cumulative sum or Kusum detector. We will talk about that. So now for stateless detector, what we do is we compute a k norm, right? Let's say there are m number of sensors. So for all those sensed values, we compute their residues, okay, and using these residue values, we can compute a norm. So let's say it can be any p norm, which is computed like this, or let's say it can be the standard. For p equal to 2, what we have is the standard Euclidean norm. So I hope everybody can identify this equation. So just set p equal to 2, it is your standard Euclidean norm, right? And for any other p, for any other your choice of norm, it would be the some ideal p norm here. And you can also use any other matrix norm, for example the infinity norm. The point is you use some matrix norm to figure out how you will compute the residue as your base method of computation, and then you will compare this residue with respect to the threshold that you may have chosen for your system. So for example, you can have this kind of a chi-square based detector. So what you do is you see the covariance of the estimation error. So you are computing the error, right, and you are, let's say this error variable is ek, and so essentially let's say you are computing the covariance of the residue, and so earlier you just computed the residues norm and compared, but now you see what is the residue sequence, and for the residue sequence you can check what is the covariance through an equation like this, right. So, we are assuming that for this error it's I mean a mean and variance of that, right. So, using I mean in that way you can compute the variance using this kind of a formula here, right. So, the estimation error is sigma e, and you are just using these weight matrices here, and you are computing the covariance of the residue like this, and in that way what you are doing is you are computing this chi-square statistics of this covariance Rk, and let us call it as Gk. So, all you are doing is you are computing the residue, and you are just using the covariance of earlier observations of the residue as a weight matrix here. Okay. So, this is your sigma r which is the covariance of this residue, okay, which you have computed from earlier observations, and then when the system is deployed online, you are using this covariance as a weight matrix here, and you are generating this chi-square statistics Gk. As you can see that this formula is nothing but you are again computing a quadratic term here with RA K transpose, then the weight matrix which is the covariance matrix, covariance of the residue, followed by RA K again, and chi-square will detect the signal to be erroneous only if this is greater than a threshold. So, this is one way, one kind of statistics that you are using, which is the chi-square statistics, and you are using this for designing a stateless detector, because again you do not have this idea of what is the previous state of the residue. We are working with the current value only, but what you are doing is you are weighting this current value with this covariance that you have already kept derived in your system. Now, for stateful detectors we already talked about CUSUM, right, that is the cumulative sum. So, this is a way to compute the cumulative sum over a window. Let us say you are using a window of length L, and over this window of length L you are just summing up the residues like this, and you are going to sound that well there is an error if this sum goes beyond the threshold. Okay. So, here you are actually using a windowed lambda square detector. So, this is not a standard sum we are computing. What you are doing is you have computed the chi-square statistics here, and you are doing a cumulative sum over the chi-square statistics, but you are not doing it infinitely, you are doing it over a window of size L. So, for a sequence of this chi-square statistics, so let me just do a small recap here. You have got the estimation error, right, and so you have you have through this expression you have computed the covariance of the residue, and then you use this covariance as a weight matrix to compute the chi-square statistics here, and then you are comparing the chi-square statistics with the threshold in a stateless manner. If you are doing a stateful manner, then you do a cumulative sum computation, but over a window of length L. So, you are adding up this chi-square statistics over this window. So, as you can see, this RA is being multiplied with the weight matrix here, and for each computation of RK, and then you are adding them up over this L length window, and you are just checking with respect to the threshold. So, this is windowed chi-square based detector. You can also have a simple summation computed over a window. So, let there be m sensors, and what CUSUM will do is it will compare the m components of the residue with the threshold. So, for this detector, so this is for a vector system. So, this threshold is not a scalar, but rather you have threshold over an m sized vector, and what you do is for each of these vectors you are computing these state values. Initially they are all 0, and then what you do is inside this window you are actually summing them up. So, as long as the summation is below a threshold value for the ith component or the ith sensor, you are summing the previous the partial sum that you have with the current residue minus a bias term. Okay. Now, this bias term would be there, so that these values are not too much too much skewed, because the sensor can also have a bias. So, to remove that bias specifically for the sensor, you can have a bias term subtracted, and then this residue value you can keep on accumulating by doing this summation, but at the same time you do not want this summation to go on infinitely, because then it is an unmanageable system. So, whenever you are crossing the threshold, that is one detection that is anyway happening. So, after each detection window, what you are doing is you are resetting this threshold, this cumulative sum for that ith component to 0. Okay. So, as you see that for k minus 1 in the previous window, it crossed the threshold limit for the ith sensor. So, in the kth window for the ith sensor you set it to 0, and otherwise you just sum up the current residue in the kth window with the previous sum, removing the bias of course, and you see that well, in case right now my cumulative sum is less than the threshold, then this is my, then I am just incrementing the cumulative sum like this. So, that is how you compute cumulative sum for each of these ith sensors in the sensor vector, and technically what you are doing is you are comparing each of them in a component wise manner. So, as an example, suppose you have two sensors. So, for each sensor you have this thing that you are computing, right. You have in the first instance R11, in the second instance R21, like this. For the second sensor R12, in the second window R22, like this you are going, right, and you are generating the statistics for each of these sensors using this formula here, and you are applying this formula as long as you are not crossing the threshold for that component, and whenever you are crossing the threshold for that component, you are resetting this statistics to 0. So, overall using the residue you are building a windowed statistic where you have this S11 and S12. In the next cycle t equal to 2, you are going to have S21, S22 like that. So, this way this thing is continuing. And what is happening is whenever one of them is going beyond the threshold, then you keep on just resetting them, right. So, it is perfectly fine that in one cycle of computation one of the components get reset, but the other does not, because for the other sensor you have not you have not crossed the threshold. So, that can always happen. So, that is how a cumulative sum based detector works, and it handles multiple sensors. So, for each sensor in that component it is adding up with the previous threshold, as long as you do not cross over the threshold in that iteration. So, this is how a stateful detector works, and we also had this previous example of stateful detection here, where it was windowed chi-square, and earlier we introduced what is chi-square at each kth step. So, all that meant was that well, you are ready with the variance of the residue, and you are generating the chi-square statistics by observing the current residue and computing this term using the variance, and then you are just comparing, and here you are summing it up over a window of length L, and here you are just simply there is no variance based computation, you are simply summing up the residues, but you are doing it for each component sensor. You are tackling multiple sensors together in a vector, and for each sensor you are computing the statistics, which is nothing but the cumulative sum, and whenever any of those computations inside the vector crosses threshold, you are just resetting it, and in that way you keep on computing the entire vector for all the sensors. So, with this maybe we will be concluding this lecture here. Thank you for your attention.